No, that's what I'm asking the technician. Is it okay in recording or I have to hold it in my hand?
recording में ठीक नहीं था
No. This is as close as possible. Is it okay?
Yes, sir.
Okay, good. Because that way I don't need to.
Is mic working?
Yeah. So should I wait for a few more minutes or should I start?
Sorry. You should start, sir. As many as scheduled.
Yeah, I mean, so I don't know whether anyone else will come or they decided that it's enough after the first day. Okay, so let me just kind of summarize a bit about what I was doing in the last session. So basically, I started with what we call copy-of-bus production function, which you can write like this after tagging long. So the main thing in here is that the addition of this extra term, which we call inefficiency. And you can interpret this as output-oriented inefficiency. In other words, this is output shortfall. So the objective of this whole exercise is not only to estimate the parameters beta 1 and beta 2, of which are elasticities. Remember, we just said, well, this indicates percentage change in y for a 1% change in x1, and then this is going to be indicating percentage change in y because of 1% change in x2. So these are called elasticities. And then again, some of those elasticities, as I mentioned, can be used to measure returns to scale. Okay. So again, we didn't go through the details because of the technicality. But you can estimate the model using maximum likelihood method, and this will depend on distribution assumption on B and E. So you can assume this to be normal, and this have normal or some other distributions. So I hope that when it gets to the left part of this data, you'll be able to see how this model can be estimated using different assumptions on the B and E term. Okay, so as I mentioned, that the whole idea is not only to do this thing, which you can get without adding the inefficiency term, but our objective is to estimate U. That's kind of the new thing in this area. Now, one side point is that sometimes people just say, well, what happens if everybody is fully efficient? So that means, UI is 0, so then again you drop this term. But again, that does not mean that there is no use of this model. Then you get the standard neoclassical model, the type of model that you learn in your textbook. Because the textbook does not talk about inefficiency. Okay. So this is kind of useful no matter whether you want to import inefficiency in your model or not. Whereas if you do DA, the whole method is based on estimating inefficiency. So if somebody says that, well, what happens if there is no inefficiency? There is no DA. Okay, but there is SFA even if there is no inefficiency, because you will have the standard model on this side, because I'm looking at them instead of. Okay, I think that was it. Okay, so this is again based on the distribution that this is normal and this is half normal. You can get a formula for this conditional mean, that is expected value of U given epsilon, and epsilon is the residual, which is the sum of V and U. So your epsilon is V minus U. And sometimes we put the subscript I to indicate that this is a cross-sectional model. And again, towards maybe in the next session, I'll get to the final model where I will have two subscripts. Okay. So once you estimate the model, remember that you get the parameters. And once you get the parameters, you can define this whole thing, okay, which is the residual. So that means you know the residual. As I was telling you yesterday, that you get the whole thing, b minus u, but the problem is separating u from b minus u. Okay, so what we do is we use this conditional mean, and because of the distribution, there is a formula for that, and this formula is again this one, and again this is, I mean, I can explain what it is, but again, if you don't need, so this is sigma star is a function of sigma u and sigma v, and this little phi and big phi. This little phi is the normal PDF or probability density function, and big phi is the normal CDF, that is cumulative distribution function. So these are some functions. This is a mathematical form of those things, right? So when you look at it, again, this is a formula that you can use, and then after plugging in the estimates of the parameters that you get from your maximum likelihood. So some people say that, well, this is a two-step procedure. This is not a two-step. You are estimating the model, you are getting the unknowns, and then you are using the unknowns to predict something. So you can say that, well, this is kind of predicting inefficiency derived from the estimated parameters. Okay. So then again, your job is done. So again, based on those things, and again, we'll be going over using data to show you how this is done. And since this is statistics, okay, we not only get a point estimate of this. So this is a point estimate, meaning that for each observation, we get an estimate of inefficiency. So if the people in this class are like 1, 2, 3, 4, I can get an estimate of inefficiency for each individual. Okay. But in statistics, we not only talk about estimate of inefficiency, but we also talk about, or does not necessarily talk about point estimates, but we also talk about interval. Right? So again, if you have any statistics background, and I'm pretty sure you have some, because again, I have never taught MBA students, but I heard that they are smart, meaning that they're good in math, right? And again, if you introduce something new, it would be easy for you to pick up. Because I also teach undergraduate econometrics, and that means they have never had econometrics before. And again, they pick those things up. So I'm pretty sure that you are smarter than my undergraduate class in the US. And again, when I talk about something new, well, you will be able to pick it up. Because we have to learn something new, right? It's not that, well, it's going to be repeating the whole thing. So anyway, so in statistics, we talk about point estimate and also interval. So again, these are formulas for interval, confidence interval. Again, this has notations like big phi, which is the cumulative distribution function. But these are functions. So it looks complicated, but these are functions. And again, a function of parameters that are already estimated. So this is kind of plugging in the estimates in the function, and no matter how complicated the functions are, when you put the numbers in there, ultimately you'll get a number, right? So these are the lower limit and upper limits of those things. So again, SCADA will give you, or R will give you, not only the point estimates, that is estimate of inefficiency for each individual, no matter those are individual students like you, or individual farmers, or individual companies, and things like that. Okay. So we talk about also efficiency. So far I'm talking about estimating U, which is inefficiency. But remember, I also talked about efficiency, which is efficiency. We said efficiency is defined as e to the power minus q. Okay, and again you can put a subscript I for individual. So then again, what is the estimate of that? Right? So sometimes we use this term, okay, that you have. So you can get an estimate of u and then take an exponential of that with a negative sign. But again, these people, it isn't poorly, so that were now statistically speaking, you should not be using this. You should be estimating this from the conditional mean of e to the power minus u given epsilon. So again, the formula in that case is going to be slightly different. Okay, so this is the formula, and again, this is the formula, right? So you can plug in the estimates in the formula to get numbers. So again, R instead I will give you estimates of U, which is inefficiency, and estimate of e to the power U, which is efficiency. So remember that if I just said, well, you are 90% efficient, that means you are 10% inefficient. So either way, you can report either U or e to the power minus U, inefficiency or efficiency. Now, sometimes people prefer to report efficiency because again, this is a number between 0 and 1. So again, if I get a number like 0.6, I know that the person is only 60% efficient. Whereas inefficiency can be between 0 and infinity. So if you get a number which is bigger than 1, sometimes we have difficulty in interpreting. Okay, so this is the reason why this petty squarely measure is more popular than the other method the other formula that I show, which goes by name JLMS or John Rule, Lavelle, Maderov, and Spick. There are 4 people who propose this method. Okay. Okay, so let me then again talk about some other applications that you can. So I just wrote this down that instead of R, you can get the point estimates, that means estimate of U, or e to the power minus U, and also the confidence interval. Okay. Now, since I'm not doing a whole lot of math, let me just try to give you some other examples that might be of interest to you. Again, given your background. So remember that Professor Ramphul was talking about this sales and advertisement, right? So let's just think in terms of the regression as like this. So I can think in terms of something that looks like this: log of sales of individual I, meaning that company I. And I'm pretty sure that if you are not doing it, you will be doing some projects for your MBA where you have to get data and again do some estimation. Because in any project, I mean, it's not going to be theoretical. Everything has to be applied. That is something that has practical implication. So log of sales, okay, so instead of sales, I'm just using log of that, okay? Because this one, if you look at the data on sales for, let's say, 100 different companies, there will be some small, some big, right? So when you look at the plot of it, there will be some way out there will be some way down here. So when you take a log, it basically squeezes everything, right? So like looking at the stars in the sky, they're way too far, but again, like when you change the scale, they are more manageable. So log is a preferred model for most of us in economics. And let's say we'll do it beta 0 plus beta 1. And let's say we'll log of advertisement expenditure. So let me just put add EXP. So this is again advertisement expenditure, and then I'm not adding anything else. You can add as many variables as you want. Okay. But again, like say VI minus UI. So if you think that well, sales does not depend on ad expenditure, but there are many other variables, you can feel to add those things. That's not going to complicate anything. So what I'm doing in here, I'm going to showing you how do you interpret your Q, and then later on I'm using this model. I'll be using this model to add variables that can explain your inefficiency. Okay. So for estimating this model, you will be looking at companies, let's say I going from 1 to n. So these are n different companies on which you have data for their sales and advertisement expenditure. Okay. So if you think in terms of Excel spreadsheet, think in terms of data like your sales and at expenditure, and then you are taking a log of this thing. So you are getting 2 additional columns to create this variable. And then again, the number of companies are going to be, and if you have 100, then your n is going to be 100. If you have 500, then n is going to be 500, right? Okay. So this is kind of the data structure, right? And then again, you take the the data, that is log of the variable in your through your R or SCADA, and then again you will be estimating the parameters. Okay. So again, you use maximum likelihood. I'll be using shorthand expression ML. Okay, gives you estimates of beta 0 and beta 1, and then again, as I said, the sigma square U and sigma square V. So these are variances. The last two are the variances of U and V. Okay, and then again, after doing this thing, you'll be getting an estimate of U hat. So I'm putting hat to indicate that, well, these are not the true values, but the estimates of the true values. And again, this is going to be based on your formula that I showed you, expected value of UI, condition on etc. Okay, or you can do e to the power minus UI. You can put a hat, big hat in here to say that what you are estimating technical efficiency, and then again, you will have a formula for that. I will show you the formula. This is the Betty-Squiggly formula for that. Okay. So you get all the numbers. So the next question is how to interpret these numbers. Okay. Okay. So let's just say that, well, you get all those things, and that job is how to interpret this. So in general, I say that, well, these are inefficiency. Okay. So let's suppose you have 100 companies and you are getting estimates of P for all of that. Right? So let's say, well, for some, again, you can get numbers like 0.01, 0.05, 0.1, 0.15, and things like that. So remember, these are how I explain this in terms of shortfall, output shortfall, right? But again, like the output in this model is revenue, right? So this is a revenue shortfall, okay? But the model is in log, right? So I cannot say that, well, this is a revenue shortfall, right? You can just say, well, it's log revenue shortfall, which is not very nice, right? Because if you say somebody to this individual companies that your log revenue shortfall is 0.01, they won't understand what you're talking about. So you have to do it in a way that they understand. And this complication is coming because of the fact that, well, we are using log version of the model. So what is happening if we go back to the model in here? So remember, this inefficiency is measured relative to the frontier, right? And frontier is the benchmark, and we are using B for that. So you can just say that, well, your sales of individual or company I, okay, divided by, you can just look at this, let me just put this frontier, then with the benchmark divided by your actual sales. And what would be this number? Is it bigger than 1 or smaller than 1? Smaller than 1, right? Because you cannot beat the frontier. It's defined as the upper limit, right? And you cannot cross the upper limit, right? Because if you do, then there is something wrong. Okay. Okay. So this is what efficiency is, right? So you can just say, well, this is again, the number is going to be e to the power minus u, right? And again, as I said, well, this is less than or equal to 1. Okay. So the purpose in here is that again, we want to get an interpretation of u. Okay. If it is e to the power minus u, that is Betty-Squiggly model, you don't have to do anything, because then you can just say, well, it's a measure of your or by what percent your sales is less than the maximum cost, right? So you can interpret it directly. But if you want to interpret EU, okay, how do we get it? Okay. So the question is, again, as I said, well, the model is in the log, and you are estimating EU. So what you can do is, let me see. So frontier is, again, you are doing like this, and you know that your expansion. Okay, so this is to be equal to 1 minus y. Okay, because this is kind of the mathematics. you can approximate a function, so e to the power u or e to the power minus u can be approximated, assuming that what u is taking a value of less than 1, because the series has to converge. Right? This is coming from, I think, high school math. Okay, so then what is u? So then now let me just write it out like this. You can do 1 minus this, sales of this frontier sales, and then again divided by actual sales. Okay, so what I'm doing is I'm just taking minus sign and then I'm doing this. So this is equal to 1 minus UI, right? Simple math. Okay. Okay. Okay, good. So just let me know, because I'm not looking at the screen, I'm looking at you and my screen again. So what is this? This is equal to u. Right? So now now we can get u, and now I have to do is what is the meaning of the left hand side? Do you see what the meaning of the left hand side is? Okay, if you don't see it immediately, let's just do this thing. So this is sales of individual I, the actual sales, minus sales, the maximum or the frontier, divided by sales of individual company I. What is this? What is this whole thing? What is it called? This is the percentage measure, right? So this is a percentage shortfall of your sales, right? So you can get an interpretation of u even though the model is in log. Okay. So I can get the interpretation in terms of efficiency and interpretation of this thing with inefficiency also. Now the other way of looking at it, let's take a derivative of this. We estimate the model, so let's just take a derivative of log of sales with respect to no, that would be coming next. Sorry about that. Okay. So then again, we can just do UI is kind of the percentage shortfall. Okay, so remember, so why did I do that? Because I was telling you before that simply UI is the shortfall in the graph. Right? But since the model is in log, it's just not the shortfall, it's the percentage shortfall. Right? So by what percentage your revenue is less than the maximum possible. So then again, if you're looking at the companies, you can just see that which companies is doing better, meaning that which company has higher values of efficiency, or which companies has lower values of inefficiency, and that type of thing. So you can rank that, or you can just look at them or do a plot, your density plot or frequency distribution, and again that will tell you how the companies are ranked over time. So if you have many, you don't want to talk about 500 companies and report all those things. You can just do a graph, okay? So in in terms of histogram, or sometimes in a smooth or histogram, which is called density plot, okay? So the plot will tell you, if the plot looks like this, so let's say your density plot of efficiency. So you have efficiency, that means your estimate of e to the power minus ui, and you are doing it against this is kind of a histogram. So this is not a so you can have a like this. Okay. So let's do this is just telling you, or you can have a spike instead of that. So let's do this is between so efficiency. This is between 95% to 90%. And then again, you have another spike in here, maybe just like this, and it might be 90% to 85% and things like that. Okay, and then again, it might be in here, something like that, and this is between 80% and 75%. Okay, so this height, as you know, in a histogram, tells you the proportion. Okay. Of companies with this type of efficiency. So this is kind of describing the whole thing after estimating the lot. Instead of saying that, well, I have 500 or 5,000, and how do I report the results? Okay, so this is not econometrics, not statistics. It's basically like a common sense of reporting the results so that people who are not familiar with any econometrics or statistics can understand. Okay, and there are many different ways of reporting these things. Okay. Um, Okay, so this is another kind of example. Again, you can think in terms of agriculture, if you are interested in that. Um, Again, as I mentioned, you might be looking at the efficiency of farmers, right? Producing a corn or wheat. So your Y is again like the wheat production, and your X or inputs are going to be land, for example, labor. Okay, I just in the US we just spell without the U. Okay, labor and then again fertilizer. Okay, and again like some other
Can I
things.
just scroll the screen actually?
Okay, sorry about that. Okay. So these are the input. These are the X. So when I write down the model, log of Y in terms of log of X, I just use all those things, and then I just get noise and inefficiency. And then again, like after estimating the one, I can get estimates of U for each farmer, and that is going to be again interpreted as, since the model is in log, if the model is in log, that would be percentage shortfall. Okay, so again, you can identify which farmer is the most productive and which farmer is least productive, and that will help. So the way this approach started in the very beginning, the early days, okay. People were talking about estimating inefficiency, and they were saying they were looking to identify who needs the help. Right? So let's say, well, after the exam, I found that there are some people who are getting below 50. Okay, so 50 is kind of the cut-off point for passing the exam. So then again, I can ask them to come over to my office, and I can talk to them that, hey, look, you are failing the course, so you need to improve. Right? So that will bring us to the second stage of the analysis. First stage is, if you think of this way, identifying who are the weak in the class, or identifying the farmer who has the highest potential for improvement, and then try to understand, like why they are not doing as well as others. Okay, so let's say, well, why are you doing the your score is not more than the score of some of your friends or people who are taking the class. So there must be some reason, right? I mean, it's not random, right? It's not random that you scored 98 and your friend got 68, right? So, I mean, after the first stage, people were, I'm just talking about the development historical. Okay, so in the very beginning, we started in 1977. So the first few years, people were doing all this type of thing. And then they realized that, well, this is not enough. Right? I can identify people who are efficient and who are inefficient. But then again, the question would be, as I mentioned before, that the student will come to me and say, well, look, I'm failing the course. Can you suggest something so that I can improve? I cannot say that, well, no, this is random. Again, I wish you best of luck, and again, take the second exam and hope to get better. That's not a policy thing, right? You have to think in terms of policy, very important. Right? How can I improve? Right? So again, like if you're talking about sales and advertisement, some of the companies you find that, well, their performance is very bad. So the question is that, well, why are they performing badly compared to others? Right? Why a particular farmer is not performing as good as others? Okay. So we have a time limit, but anyway, when it stops, then I will also stop. Okay. So again. So the next step is talking about determinants, or what are the variables that can explain your inefficiency. Why your score is less, or why a farmer is doing much better. Let's say, well, I'm looking at the farmers in Haryana, this particular area. So you cannot say that while you are comparing, farmers in Haryana with farmers in West Bengal or Bihar. Then again, like there would be something else, and I'll be coming to talk about those things also. So let's just that for simplicity, so that what your data is from this region. Okay. So then again, you might be saying that okay, these are farmers that are all cultivating wheat, and I still find that some are not as good as others. Okay, as good meaning not as efficient as others. So then you started saying that okay, so what could be the reason? Okay. So you look for variables that can explain those things, and we call those things Z variable. Okay, so this is kind of a notation of that. Y is output, X is input, and Z is this variables, which we sometimes call environmental variable. By that I mean the variables that can that are associated with the production environment, not kind of the other issues, not like pollution and other things. I'm not talking about those things. I'm talking about production environment. Right? So let's just look at one thing at a time. Okay. So again, in the early period, what people will be doing is they will estimate the model, the stochastic frontier model that I introduced. That means assuming U to be IID, identically and independently distributed, get an estimate of U, and then again regress. They will run a regression, estimated U on some other variables. Now that's bad. As we always say, you never ever do that. Why is that bad? Because you are assuming U to be IID. It's not related to anything. Right? And then as soon as you are done, you are just saying that, okay, let's explain that in terms of some other variables. You are contradicting yourself. How can you say that, well, it is not dependent on anything, and then after estimating it, say, well, let's try to explain it in terms of other variables. So this is completely contradictory. Okay, so there is no need to do that. And again, in the early days, meaning in the early 80s, people would be doing those things because the computer programs were not good enough to estimate the model. Okay, so nowadays, and we just say, well, that's not necessary. We can think in terms of like making U in efficiency function of some Z bit. So what we do is, you can just see that in here that is abnormal. So if we think in terms of this, let me highlight that. There is EU before it was n plus is abnormal, so we put the plus to say that well, it's only the positive side of the distribution, not the negative side. Okay, and then sigma square U was a constant. Now we just say, well, this is a function of some Z variable, right? And because this is a variance is always non-negative. Sometimes, or most of the time, programmers use exponential function. So it's just written as e to the power z delta, meaning that well, e to the power delta 1 z1 plus delta 2 z2 and things like that. So remember, the z variables are determinants, and determinants will depend on what type of example you have. Okay. Okay. So then again, like what we do is the advantage of doing this thing that now we can go to the estimates of inefficiency and look at the formula that I have over there. Okay. So you can look at this formula, but then again, like in this formula, your mu star and sigma star will not be constant. It would be the function of the z variable. This is going to be somewhat complicated when you look at it algebraically, but again, it's all derivative. We'll be taking a derivative of that. Okay. So the idea is like this. Let me just write those things down in here. Okay. So let me just create a page in here. Okay, so we get an estimate of U. So now we are just saying that well, U in efficiency, okay, is a function of Z variable or variance, right? Okay, and we specify it in terms of sigma square. So sigma square U is a function of Z, and we just say well, this is exponential function of delta 1 Z1 plus delta 2 Z2 and things like that. Okay, so you can have one or many variables. Okay, so we get an estimate of U using the same formula. So that would be a function of Z. And then again, our interest is to see this. So let's do it. That means if you increase your Z, what will happen to your inefficiency? Okay. And remember, since the model is like this, okay. So again, like your derivative of y with respect to z is the same as because as this. So when you just say, well, I'm interested in the derivative of z with respect to, derivative of u with respect to z is the same as derivative of y with respect to z with a sign change. Okay. So the interpretation of after estimating this, we are interested in the marginal effect. That means if you increase z by 1 unit or 1%, depending on whether it's in as a log or not, by how much your output will increase. Okay. Okay, so now let's just go to specific examples that I was talking about. So let's just look at the model cells. Okay, so your y is 6. Okay. Now, can you think in terms of some variables that can explain inefficiency in the sales advertisement relationship? Just any variable that will make sense. Why a particular company is less inefficient? Can you give me some reason or some variables that can explain why a particular company is performing better than others?
Their sales policy, their promotion policy.
Okay, so it's just about promotion. Sales is the ultimate, dependent variable, ultimate variable that we are explaining, and we are using only, advertisement. Okay, so it's just about promotion policy.
Credit policy also is like
Policy of what?
credit policy. So
Okay.
how much time the credit?
Okay, so the credit, what do you mean by credit policy? I'm just trying to understand.
So for what time they give their debtors to repay them?
Okay, so basically the way I interpret it, let me know whether I'm getting you right or not. So let's say, well, these companies are taking money from the bank, okay? And banks sometimes, again, the way the banks operate. If you are big and you have reputation, then you have no problem in getting loans. But some other companies may have difficulty in getting loans, right? Okay, that means they don't get as much as they ask for, okay? So what is happening is that, well, if you think of that as a credit policy, so you say, well, okay, whether this particular companies are facing what we call credit constraint. So let's just use another term. That means whether they are facing credit constraint or not. Okay. So let's say what you are measuring credit constraint in terms of some variable, right? Or credit policy or whatever you are thinking in terms of. So that's kind of the Z variable that you have. Okay. And you can think in terms of some other variables, something like R&D. That is whether these companies are spending anything on R&D. If they spend in R&D, that might be they might be more they might be performing better. Okay. So again, I'm just throwing some variables to make it a little bit more practical instead of saying that well, think as of Z, Y, and X. Again, like the way I teach again on my 466 class, this intermediate or undergraduate econometrics, I give them a lot of examples, okay, just to make sure they relate the Y, X, and Z variable to something in practice. Okay, so then again, the model is again like the only change that is in the model is now U is a function of Z. Okay, so we just said about inefficiency, is not IID. It's depend on some of the Z variable. So again, like we can assume U to be a half normal. So the distribution of U, and I'm not using the subscript I, but that should be there. So n plus again is half normal, and then again mean 0, and then again your sigma square is a function of Z. So what is happening if you think in terms of doing a graph that will illustrate the point you can think in terms of many of those have normal distribution. Think of one like this with a particular value of z, okay? And then again, you can have another one that might be looking like this for different values of z, okay? So they all have not, I can keep on drawing some more. Again, I am not very good in doing that. Let me just do something like this, okay? So you can just have a series of those things, and these are specific to the values of z. So if everybody has a different value of z, then everybody will have their own half normal distribution. So remember, this is half normal distribution, meaning that well, it has a zero mean and some variance, but the variance is dependent on the z variable, which is specific to individual. Okay. Now it may not be specific to individual. You can think in terms of groups. Okay. That means it's the variance is different for different groups. Okay. So this is kind of the rationale for doing all those things. And then again, after estimating the model, as I said that well, you will be interpreting, you will be first reporting inefficiency or efficiency, and then you will be looking at the marginal effect. Okay. So let me just create another page in here. So then after estimating it, you get the marginal effect, that is derivative of your hat with respect to, okay. So remember the interpretation of u hat, you can do that, or you can just say the derivative of e to the power minus u with respect to z. Okay. So when this one is telling you that if z goes up by 1 unit, okay, or 1% depending on how you measure z, okay, by how much your efficiency is increasing or decreasing. Okay. All right. Do you see the practical relevance of this thing? And again, you can think in terms of now going to the format. Let's say the inefficiency of the format will depend on percentage of this farming example. Let's say that Z is the percentage of family labor. So do you think that one family labor is more productive than hard labor? Yes or no?
Yes.
Yes, I mean, I don't know the background of some of you, but assuming that well, you have some idea about the farming, then we tend to believe that, and again, there are reasons. You just go and take a look at these things. If you own, if you are the owner, you'll be, maybe if you smoke, you will take a smoking break, but as soon as your cigarette or bidi or whatever you smoke is over, you'll get to this thing. Whereas the other people will be, taking much longer time to. So we always tend to believe that family farmers or family labor is more productive than hard labor. And again, like you can. This is not just a view. You can empirically estimate whether that is the case or not. So let's say well, Z variable is percentage of family labor, and then again you estimate the model using Z as determinants of inefficiency. So you go through the same routine and you plug the data in a computer, right? Computer gives you an estimate of you and also gives you again the marginal effects. So it will give you this and or this. So again, if you feel that well, the interpretation is easier in terms of this, you can just report those numbers. So again, the data will give you the marginal effect of this thing. Okay. Now again, the formula I'm not getting into those because remember the estimate of B when you look at it, the function looks quite complicated, but it's derivative, right? So how difficult can it be? I always tell my students that well, don't ask me to do the derivative. I know how to take the derivative. It's your job to take the derivative. And if you are not sure, then you go to MATLAB and check with your calculated derivative with the one that is built. So again, these are complicated functions, but again, we are taking a derivative, and we all know how to take a derivative of a function. Right? So the interpretation of this thing that if percentage, remember this is already a percentage. So then again, we just say, well, if the percentage of family labor goes up by 1, that is 1% increase in family labor, what happens to your efficiency? Does it go up? And if it goes up, by what percent? So these are all kind of interesting things. Okay, interesting things meaning if you can get data on those type of things and estimate the model, this can be published. Okay, I mean the reason is that while in agriculture, I mean getting data for this type of thing is sometimes difficult. But I know that such data exists. And as I was telling you that I don't know many people in here, and I don't know the sources of data. But there are many people who are using Indian data, and they are doing something mostly on manufacturing. Very few people work on agriculture. Right? But again, if you are doing manufacturing, you can do similar. So these are different applications. It doesn't matter whether you are doing in agriculture or manufacturing. Now, as for me, it depends on what type of data is available. If it is agriculture, I have some quotas in Norway. I ask them whether they have this type of information. And again, I write papers with them because they have data on dairy farming, crop farming, and many other things. Manufacturing, I use data from China, and we're trying to get a hold of some data from India, but now we are having some difficulty in getting the data, even though we are paying money to that. Okay. So monitoring Indian economy is a data source. I mean, this is not free, but many of the universities in India they are members of that, so you can get those type of manufacturing data free. It meaning that you don't have to pay anything. Okay, so this manufacturing data again, you will have the manufacturing output, whatever that is. You can just look at SIC code type things. So it can be electronics, it can be chemicals, it can be garments, it can be footwear. So again, these are all classified. So you get the revenue measure, how much the revenue is generated from each of these activities, and then again correspondingly how much capital, how much labor, how much materials are used to produce those. Okay. So again, when it comes to application, you can think of many standard applications, and then I have a separate section I'll be talking about later. That means if you just say, well, I'm not into production economics, can you give me some examples where I can use this type of techniques, this type of tools? There are many applications where you can use this as a tool. It's not a measure of efficiency. We don't interpret it as efficiency, but again, like we'll have a EU, which is one-sided. Remember, it's just truncated, meaning that it does not take any negative values. So again, like the possibilities are much more than production. So nowadays, I try to do that. I just go, look, don't think that you have to be a production economist to apply this tool. So you can be a health economist, you can be labor economist, and still you can use this type of tools. Okay, so I'm just saying that whether it will start me off. Okay, so let me just go and then add something more to this. Okay, so far what I did is I talked about half normal. So again, remember the definition of half normal. You have a normal distribution with zero mean, and again, like if you cut it at zero, it becomes half of the distribution. So this is one way of explaining half normal. But remember, U is at one-sided, meaning that U is greater than or equal to zero. We are not saying that whether the distribution of U will have a zero mean untruncated before truncation, okay, or again positive or negative things. So more general approach is to say that U is truncated now. What do you mean by truncated now? Let me just show you some graphs. Okay, so a half normal is like this. So U, think of U as a normally distributed random variable with zero mean. Okay, and then you cut it into half. That means you just take it on this side, right? which I highlighted. So that's half normal. But what happens if U is normal but not zero mean? So it has a mean mu, and mu is positive. So then again, you can think in terms of a distribution like this. The mean is here, mu. Okay, it's not zero. And if it is positive, then zero has to be to the left of it by definition. So then again, like this is the part which is relevant. Okay. So the other thing is that, well, what happens if mu is negative? So the mean in here, which is negative, so the zero has to be to the right. So the relevant part of the distribution is this. So you can think in terms of generalizing the half normal. Half normal is restricted because it's assuming that, well, the distribution of U is half of the distribution of a normal variable with zero mean. But the mean can be non-zero, and here I show that in terms of positive, how it will look like, and in terms of negative mean, how it will look like. Okay. So then again, the rest of the story is very similar. Okay, let me show you this graph. So this is just showing different values of mean. Okay. So for again, when you are changing mu, what is happening? The distribution is changing. So I was telling you that a half normal is more, more meaningful, because half normal means most of the forms are close to fully efficient. So this is your inefficiency. Right? Now, if you just say that, well, this is not half normal, this is truncatedly normal. So what is happening is the percentage of form with near full efficiency is not as much as percentage of forms with some inefficiency. Right? Now that might happen. It might be kind of an empirical question, or if you have more insight, then you can just say, well, look, here half normal is not relevant because I know that most of the forms are inefficient. And like in the context of India or other countries also, we talk about public versus private enterprises. So we always argue that public is not as efficient as private. Right? And there are many reasons you don't feel the incentive. You have a permanent job and nobody can fire you. Well, things are changing, but in the private sector, no, that's not the case. If you are performing badly, you'll be fired. But in a public sector, it's very difficult to fire somebody. Right? So this is kind of an incentive problem. Right? So people don't feel the incentive to work as hard as they would be doing. So again, like if we are doing this type of exercise, and people have done this exercise not in the context of a stochastic frontier, but in terms of using a dummy variable type thing. So you categorize the forms into public and private, and you put a dummy variable, and you see whether the dummy variable coefficient is coming up with a negative sign. So that again, the public forms are less efficient. But here, if you want to use that example, you'll be using public or private dummy as determinants of inefficiency. So this is going to be more outside the world from a technical point of view. Is much better model than putting a simply dummy variable in your regression. Okay, so the other case where you might have this type of situation, okay, that means the percentage of form with some inefficiency is a lot more than percentage of form with very little inefficiency. Is again when the forms are regulated, is exactly the same thing. Or you can think in terms of nationalized versus non-nationalized. Okay, think of railways. Okay, this is one good example. Or banking also to some extent. Do you think that well, banks has an incentive to do better? Not necessarily. Like some are saying that okay, my job is, the manager is thinking that well, my job is permanent. What they can do most is kind of transfer the manager from one branch to the other. But other than that, there is not much that can be done. So the manager may not have the incentive to do as much as possible. And remember the whole idea when we just about why there is inefficiency. Remember the graph that I drew? then I ask you, is it possible to produce less than maximum? Of course, we all know that, right? You just have your cell phone and your computer is on and you just checking your messages in the or doing some chatting with friends and that type of thing. So even though official, you are working for 8 hours, for example. Again, if I adjust those things in terms of what is the time that you use for doing something personal, then it would be probably 6 hours or 7 hours. So then again, you are not putting your maximum effort. So you can think in terms of those type of ones. So when I just said about potential for application of this type of model, again, in reality, again, all you have to do is come up with an interesting application. Okay, interesting in the sense that whether people will be saying that okay, this is something interesting, or this is something that maybe we all know, but again, like the idea here is to quantify. Right? Remember, we always use the word inefficiency. You are traveling by train and you said, well, this service is really bad or inefficient. You're flying and you said, well, this is inefficient. But again, here we are kind of giving a proper definition of what do we mean by saying that well, the airline is inefficient. Maybe they were running late by 5 minutes or 10 minutes, or maybe that their food was not good. If you are asking for food, I think Air India provides some food, but again, the other airlines you have to pay. And then again, the other services, whether the host, the employees in there are treating you, how are they treating you? You ask for something and they come back, and after 5 minutes, and you get really irritated. Say, well, why should I wait? So this type of things. But again, here we are quantifying those instead of simply saying that okay, this airline sucks, this airline is not good. We are just saying that why is it not good? Okay. So again, for airlines, we cannot get many airlines in here. So this type of studies may not be very good because we have only how many airlines are in there? There are only few, right? So again, like this requires at least quite large number of observations. Right? A large meaning that it does not mean that you only have to have 100 or 200 or 500. But if you have only 3 or 4 or 5, then this is not very good. Well, DA people claim that they can do it with 5 or 6. We can do it also, but then people just said, well, since you are doing econometrics, your estimates are not very robust. Okay. So that's kind of a different ballgame. You criticize others by saying that there is no, it's not very robust, or the standard errors are high, but in DA there is no standard error. So the question is, I often just say, well, which one do you feel? With your eyes open or eyes closed? Eyes closed, you don't see anything and everything looks good, right? With eyes open, you see things and you say, oh, no, I don't like it. It looks bad. So it's that type of comparison. So I just said, well, this is nonsense to argue that SFA requires more data and DEA doesn't require more data. Well, it does something, and again, like SFA will also do the same thing. But then again, people criticize SFA because they see certain things, they have their eyes open, but in DEA, the eyes are closed because there is no way of getting the standard errors. Okay, so this is the story. So what I have done so far, I just briefly talked about modeling inefficiency using normal for the error term, and then again have normal or truncated normal for the inefficiency term. There are other distributions that you can use, or there are other distributions that people have used. So these are exponential distribution, and then exponential, and then there is also some other distribution that are not that popular. So the popular distribution have normal, truncated normal, and exponential. The reason for that is you can get a closed form expression of the likelihood function. So when you do maximum likelihood, it's a function without no integration. But if you are using other distribution, then you won't be able to like get a closed form. That is, you have an integration sign sitting in the function. Okay. I mean, it's not a problem, especially nowadays, because the computers are very powerful, and there are programmers who can deal with that type of function. So first, you have to evaluate the function numerically instead of remember that in your calculus class we are asked to. I mean, in a homework problem, we're given a function, it's about integrate this function. Sometimes some of the functions are easy to integrate, sometimes it's difficult, and sometimes you don't know whether it can be done or not. Okay. But nowadays people don't care that much. They don't learn those tools that we learned in high school or in college, trying to say that, well, how do I integrate this function? They say, well, you don't worry about it, let the computer do the job. Right? That means you do it instead of analytically, you just do it numerically. Okay. So then again, coming to so this gamma distribution is something that Bill Green uses. Probably know the name. He has a textbook which is very popular, and he's also the author of a program called LibDAP. Okay, but again, LibDAP is not as popular as other softwares like R or Standard. Okay. Okay, so to summarize this section, let's just say that so what I did so far is that I just said that in principle one can use any distribution on U, provided that U is this non-negative. So that is the only constant because we are defining inefficiency as short form. So it has to be one-sided. Right? So the question is whether again we agree on the distribution of it. And this is kind of a staking point. Many people don't like SFA because this is what you are assuming abnormal. I don't trust that abnormal is the right distribution. I don't trust whether it's exponential. Right? So that is again like an issue. Okay, but again, I'll talk about that this is not necessary to assume distribution. So again, as I said about abnormal, Hungarian normal, exponential, these are popular because we get a closed form expression of the likelihood function. Okay, but that is not necessary. Okay, so what is necessary that we need to assume a distribution for even t based on what I did so far. Okay, now the distribution of V is not debated. Why is that? Because it's a kind of noise, and everybody says that if noise is distributed normally, usually they don't complain. But the complaint is mostly in terms of a distribution of inefficiency. Okay, so what we are doing in the recent years, last 5 years or 10 years, we are trying to get rid of the distribution assumption. We are just saying that is it possible to estimate the frontier mark, stochastic frontier mark, without using any distribution on it? And the answer is yes. All you need to do is you have some distribution, but we don't know why. So remember, I didn't put n or something like that. So u has some distribution with mean, okay, mu, and this is a function of z. So you have to have some determinants, and this z is different from x. Okay. So if that is the case, then again you can write expected value of u is a function of z, and let's call it h. And then you have the f function, which is the production function, and then h function, which is related to inefficiency. And x is different from z, so you can think in terms of running a regression with two sets of variables. You have dependent variable y and x variables, which are inputs in the production function, and the z variables are determinants of inefficiency. So this is quite simple. So the only thing is that you have to have some z variable. But then we say that that should be the case always, because whenever we are talking about inefficiency and trying to explain it, you have to explain it in terms of some z variable. You're talking about policy implication. What is the implication of having more R&D? Or what is the implication of having more family labor? So if you don't have anything like that, then again, as I said about students come to me and say, okay, I do not suggest anything. You just, I wish you best of luck and your next exam. Hope that your next exam will be good. Now, you have to give a proper guidance in terms of what can be done to improve efficiency. So let's say, well, if you are advising the farmers, you have to tell the farmer who is not as efficient as his neighbor that, well, look, you are not doing this properly. Do these things properly. You are not putting the fertilizer in the right time. You are not doing the irrigation at the right time. So these are some of the policy variables or the things that you can suggest to the farmer to improve their performance. So from a practical point of view, there should be always some Z there. So that this should not be treated as kind of a bad thing. It is a good thing. We did it in the very beginning without Z variables, but nowadays everybody is talking about inclusion of some Z variable, and these Z variables are policy. So if this is the case, then we can estimate the model without any distribution. Okay. So now again we are heading to a situation where we just say, well, no, if you don't like the distribution, that's fine. I can prepare a dish for you, even if you don't like the preparation that I provided you. So I just give the example in terms of menu. You go to a restaurant, there are some menus, and you say, well, I don't like. Like I was saying that you're complaining, going to the canteen or the restaurant where I'm staying, the guest house, and they have the same thing every day. This is the third time I'm just having parota as a breakfast. Well, this is good because this is very nice, but I try to look for alternatives, right? Because I'm in a different part of the country. I want to explore different type of food. So the menu, I just typed it to a different menu. So I just said, well, if you don't like it, you tell me what you want. If I am a chef, then I can cook something for you. So this is the message that you don't have to say that, well, I don't like abnormal. That's fine. Tell me what you like. If you say that, well, I don't know what I like, then again, of course, you are out. Right? You have to say what you like. Okay? And then I can prepare the dish for you. Okay? Okay, so let's just stop it here. And then again, after, I don't know how long the break should be, at least 15-20 minutes. There should be some coffee. Right? At least that's what I was told. That always will be tea or coffee break. And then again, like I'll start with the panel model. Okay, so I'll be repeating some of those things, but again in the panel format. And assuming that while you don't know panel modeling, I'll be following my undergraduate econometrics course for the first 10-15 minutes before I go to this board. So again, as I said, I'm trying to adjust myself to the need of the participants like you, because I was prepared to do this. Okay, because I told you that, well, I'm used to teach this course to the researchers who has already have PhD, the assistant professor or so. But now I started facing that it is an MBA student and they don't have econometrics. So I'm adjusting myself to do it in a way that it makes some sense. Okay, so I'm hoping that you are not completely thrown out in the water, deep water, and you don't know how to swim. Right? Okay, so let's just take a minute. Okay. I'll continue talking about panel model for this session as well in the afternoon. So the first thing, okay. So the first thing that what do we mean by panel data? So far we're talking about cross section of data, and by cross section we mean again individual firms or individual companies observed at a particular point in time. Okay. So now we are bringing time aspect of it. Okay. So one way of viewing it is that it's a time series of cross sectional observations. So you can think in terms of, like, let's say you are registered in a MBA class. So there are 30 people in this class, and then you are meeting in like 30 times over the semester or over the. So again, we have two aspects: individual enrolled in the program, and then again you are going to the class for a certain number of time periods. So there are two things in there. One is individual I, and this can be company or farm, agricultural farm, or again like manufacturing farm. Okay, many other things that you can think of. And then again, so this will go from, let's say, I equal to 1 to n. So there are an individual, like farms or companies at a particular point of time. And then again, we have another substitute t for time. So let's about t is going from 1 to 80. Okay, so these are the time series aspect of it. Okay, so again, this panel data is loosely defined in many ways. One is again as I see that this is time series of cross section. So you can think in terms of let's say an Indian states. This is your cross section, and then again time series is the years of observation. Remember, I was giving example, but you can think in terms of the states, just to see how the states are performing. I give you the example of Bihar being treated, quote unquote, unfairly as the backward state. Maybe there is some truth to it, but we want to figure it out instead of listening from other places about how backward the state is. Okay, so we want to quantify that. So this is one way of defining a kind of model. So whatever variable you have, we put in two subscript. First of all, y is the outcome variable. So then again you can put I into. So if y is sales, then again sales for company I at a point in time t. Okay. So if you fix the company I and then look at the time series observation, that's going to be showing you the dynamics. Okay, of what is happening to the sales over time. Okay. If it is agricultural production, then again you'll be looking at the production of wheat or corn or bajra or jowar or whatever product you are looking at over time. Okay. So first thing is that one is two subscript I and T. Okay. Now the second question is whether you have the same T. So T exactly the same for all I. What do you mean by that? That means we observe the same components throughout all the time periods, right? So this is what we call balanced panel. Okay. So now again, I noticed that on first day that we see a study, there were a lot more people. Okay. So I don't know whether they will be showing up tomorrow or not. If not, they are observed only for one time period, right? First day, or maybe just two lectures. So again, if I just count the number of lectures, okay, then they will be attending only two lectures, whereas others might be attending all the lectures, right? So the number of time periods, okay, for which they are going to be encoded in the data is not going to be exactly the same for all. Okay, so T is not exactly the same. You might say, well, T has a subscript I to indicate that number of time periods for which the individual I or company I is observed. Okay. Now there are maybe many reasons why a particular company or a particular farm is not observed all the time period, right? But again, we are not getting into the details as to why they are not. It might be missing randomly, or there might be a particular reason why they are not reporting the data for every year. Okay, so the techniques that we are going to be talking about works for both balanced and unbalanced panel. But again, like dealing with unbalanced panel in terms of notation is a little bit cumbersome. Okay, so what we will be doing is we'll be assuming that you have a balanced panel. That means, we observe every individual for all the time periods. Okay, this is kind of a simplification. And again, as I said, mostly we do it just for notation of convenience. Okay. Now, before getting to the stochastic frontier model using panel, let me get to some other details about it. Okay, so the first question is that what do you gain by having a panel? Okay, so the first thing that you just see that you have I and T. So if I is equal to 1 to n, okay, and T is running from 1 to big T, then what is the total number of observations? Is equal to what? N times T, right? So again, in a cross section, you have n observation, but in a panel, you have n times T, right? So if n is equal to, for example, 100 and T is equal to 10, then again, you have 1000 observations. So the first thing that if you have a panel, the number of observations increases automatically, right? Okay. And again, in econometrics, the number of observations is very important. If you have the more observation you have, the better the estimates are. So we always say that it's good to have more observations. Okay. So the other thing from again statistical point of view, remember we are estimating parameters. The true parameters are known. We never know how far we are from the truth, right? But one thing we know from a statistical point of view, that the distribution of data had, the estimates, is going to be getting closer and closer in some sense to the true parameter as the number of observations increases to the population or increases to. Okay. So that's basically what the advantage of having a panel is. There are some other advantages, and one other advantage that is very important in modeling panel is that it can control individual. We just use heterogeneity. What do we mean by individual heterogeneity? Okay, so I'm looking at you guys. Do you think that you are all the same? No. Everybody is different in some way. So the question is, when you model it, we want to control for individual idiosyncrasy or individual heterogeneity or whatever term you want to use. Okay. Some people might just say, okay, you are crazy in some respect. So the question is that, if you are crazy, I want to like a control for your craziness or my craziness or someone else's. So again, with the panel, we can control for unobserved individual effects. Okay, it's not that we always observe why you are different from him or he is different from him or he is different from me. Okay, we know that we are different. Okay, but we cannot explain what is causing us to be different. Okay. So then again, what is happening is, if you look at the model, again, you can look at the sales model that we were talking about. So let's say log sales or simply yi. So yit is equal to, remember I was writing it as beta 0 plus beta 1 log of advertisement expenditure. And then again, I'm putting int and let's say put vit. So there is no inefficiency for the time being. I'm just kind of explaining the model. Okay. So this is the standard cross-sectional model. You can use it in a panel because again I just told you that you have more or data to estimate the model. So your estimates are going to be much more precise. Okay. But we want to say that there is something else that we can do with pattern. So now this is constant. This is exactly the same for everybody. Okay. So now we just say, well, how about having something like this? Let's just say that this is alpha I. So this intercept, okay, beta 0 is not exactly the same for everybody. So we all have separate intercepts. So this efficiency that I'm talking about is controlled through the intercept. Okay. So what it means is that if you are looking at the graph of it might be looking like this. So this is for individual 1. This is number of cells. And here you have advertisement expenditure. Again, log. So let's just put log. Okay. And this is for I equal to 1, company 1. And then for company 2, it might be something like this. Let me just change the color. So this is another advantage of having the pen in here. You don't have to look for a different color chart, right? And then again, like for company 3, it might be something like this. So what is happening? These lines are parallel. Why they're parallel? Because beta 1 or beta 1 is exactly the same for everybody. So the slope is not changing from individual to individual. That means the marginal effect or elasticity of advertisement expenditure is exactly the same for every company. But every company has kind of a different intercept. Meaning that this company may be different from other company. Maybe they're big or they have different reputation in the market. You can think of many different things, right? And if you're looking at individuals, then of course we can just say that individuals are different in many different respects, and we are controlling the differences through the intercept. If you are looking at agricultural application, and again these are Haryana farmers, again farmer 1 is not exactly the same as farmer 2, even though they have same quality of land, they're using same fertilizer and things like that. Okay, so sometimes we explain that in terms of management. That again, management or managerial ability of different farmers are different, right? But again, management is something that is not observed, right? We don't have data on management. Right? Nowadays, again, there are people who are doing survey to figure out, some idea of management. Okay. But in general, whenever we talk about management, we just said about this is something unobserved. This is just like ability. We always say that, again, we run a regression on wage, on ability, and your education. But ability is something unobserved, right? We all know that ability is related to smartness. You are smarter than him. But again, do you have any data to prove that you are smarter than him? No. Okay. So the question is that, can we control for those type of things, unobserved smartness, or unobserved ability, or unobserved management? Okay. So long as you assume that, that is not varying over time. So if you're smart, you just stay smart for the whole time period. If you're opposite of smart, I know what it is. I'm not using that term. You stay that way the whole time. Now that is also bad because again we just said you may not be smart to start with, but again over time you can increase your potential by doing practice or that type of thing. But let's make this assumption that this is time and date. So when you're looking at the companies, different companies are different. Okay, so we just say this is company specific effect. Alpha I is an effect specific to each company. Now we cannot control for that in a cross section because we are observing the company for only one side. But if you observe the company for more than one time, then you can control for those things. Think of putting a dummy variable for each company. And you can do that because each company is observed for more than one time. Right? Okay. So this is an advantage of having a panel. So again, as I said, you can in this simple case, you can just draw 3 different lines or one line, and that is basically showing that intercepts are different for different companies. And it is a controlling for individual or company specific heterogeneity without knowing what is causing this heterogeneity. Okay. Okay, so again, I'll get to the efficiency in a few minutes. Now let's say that you are not doing these things. You know that there is heterogeneity, right? But what happens if you ignore it? Okay, we always ask this question. Whenever you come up with a new model, the first question that people will be asking is, what if you don't do that? Right? Okay, that's kind of the fundamental question. Whenever you do any kind of research, okay, or any kind of study, the first question that will be asked is that what, why are you doing it? What would happen if you don't do it? Okay, so just to illustrate it, let's just look at this graphs. Okay, so let's just look at the. I'm just drawing it up. Yeah, just look at the figure 1.1. Okay. So this little thing that you see at this at for each individual, let me use the highlighter. Okay. So this is basically data for individual one or company one for different time periods. So you have dots in here like this. And then again you can see that well you can connect the dots and get a straight line like this. Right? So this is basically what I was doing it in here in the graph. That means this is for individual one or company one. Okay. And then similarly, you go to company 2 and company 3 and company 4. So you can see from this that again, like you can connect these things and say, well, these are heterogeneous intercept, right? Okay. Now again, like you just take all those things out, and all you just see that is the basically scatter plots like this. So if you believe that there is no heterogeneity, okay, and estimate a model, okay, or estimate a linear regression, what would you get? You will get an estimate that is given by this heavy black line. Okay. Now compare the heavy black line which were estimated with the truth. These are the true lines. Okay. So what do you get? Okay, your estimate of the slope given by the heavy line is different from the estimate of the slope from the individual lines, which were the truth, right? Because this is what data is generated from this individual effect. We all know that different companies have different effects, but we are not capturing it in the model. So you are getting a filter line that looks like this black line, which is not representative of any of them. Okay, so this is one graph. So now let's just look at the second graph. Okay, what is happening in there? So the relationship in there is the again, like this is still positively sloped. Okay, these lines. Okay, but the intercepts are negative. Okay, so that's kind of the difference between these two graphs. Okay, so now again, I remove this lines, and then again think in terms of fitting one line through all the data points. You will be getting this again this black line. So what is happening in here? The slope is the estimated slope is bigger than the slope of the individual lines. Okay. So again, you are misrepresenting. You will be coming up with a different effect of advertisement. You will be saying that well, the effect of advertisement is a lot more because the slope of this line is bigger than the slope of this thing. So you'll be saying that okay, advertisement is very effective because you are getting a much bigger number than what the truth is. The truth is when you control for other individual effects. Right? So you get a very different picture. Here is the opposite. Here you'll be getting an estimate that's less than marginal effect. The slope is less than the truth slopes. Right? So these two graphs is again one case you are showing that what you will be over representing or overestimating the true effect, and in another case you will be underreporting or underestimating the true effect. Now look at this third one. Okay, so here again like these are individuals, right? And they are again like they have positive slopes, right? And then again like if you combine them and again estimate a single relationship, okay? Assuming that while you don't know how to handle panel model, so you are just doing regular cross section, and then again your estimated line is going to be looking like this. So what is happening? The true slopes are all positive, and the estimated slope is negative. So now it's completely different. Right? You will be saying that well, okay, advertisement is bad because it's not increasing sales, right? It's basically reducing sales, and that's because of the fact that well, you fail to control or company specific effects, right? Okay. So now again, there are more graphs on this one. So now let's look at one. This is the relationship for company one. This is the relationship for company two, and this is company three, and so on. And then again, like if you look at the scatter plot and try to find out the relationship, so you'll be seeing points like this all over. So what happens? Do you find any relationship? If I show you this thing, you'll be saying that well, there is no relationship, right? Because everything looks like a circle. Right? But there is relationship. The only thing is that well, for some it's positive, for others it's negative. And when you're looking at all of them together without control for individual effect, you say that well, there is no effect. Right? Okay. And then again, you can get a similar picture from the last one. And again, for individual one is positive, positive, positive. And again, these are all positive. But again, when you combine them, you'll be getting something very different. So these graphs again illustrate the point that when the true data generating process or the true relationship, okay, has different effects for different individuals in terms of their intercepts, right? Or what we call individual heterogeneity. And if you ignore it, you might be, we don't know which situation you will be in. These are different illustration of different scenarios. Actual data, we don't know what scenario it is. But often it happens that you get wrong sign on some of the parameters. This is because of the fact that you fail to control for individual heterogeneity. Okay? So this is what we start with. Whenever we talk about panel model, we start with always this type of scenario that look, I mean, in a panel data setting, if you're a panel data setting, first thing you should be doing is controlling for individual effects, right? Because without controlling for individual effects, you might be getting a relationship that is nonsense here. Okay. Okay. So now again, like okay. So let me just see how far. Okay. So I think we should stop, right?
Yes, sir. Yes.
So anyway, this is a good point because what I did only in it so far is that I introduced that idea, okay, to the structure of it. I was thinking of going over a little bit more, but again, like I can do it after lunch. So again, the plan is to come back and use the panel model to show you that when you have individual effects, how do you estimate the model, and then we'll be going over to efficiency model. Okay. With this time will be, I think, I hope to maintain time because this is also something whenever we talk about efficiency, I always say that maintaining time is important, right? Because otherwise you are wasting someone else's time, which means this is misallocation of our resources, right? Either your resources or my resources or resources of some other thing. Okay, so okay.
Thank you so much, sir, for sharing your knowledge. Now, I would like to invite our one more expert and esteemed faculty, Dr. Jogendra Kumar.